hire from a no hire. Let's get into it. Before we start drawing boxes, let's talk strategy. Every system design interview for a user-facing product should follow the same four-step roadmap. Step 1. Define requirements, both functional and non-functional. Step 2. Identify core entities and APIs. Step 3. Sketch a high-level design that satisfies your functional requirements. Step 4. Deep dive to tackle scale, reliability, and hard engineering problems. This framework is repeatable. It works for Dropbox, it works for Uber, it works for Twitter. Internalize it. One thing I want to flag early, Dropbox is considered a slightly easier system design question, so it gets asked heavily at the mid-level E4L4 range. But it absolutely shows up for senior and staff candidates too. The difference is how deep you go in the deep dives. I'll call that out as we go. Alright, step 1. Let's define our requirements. Functional requirements, these are the core features. What does the product actually do? In an interview, you always want to identify the top 3. For Dropbox, number 1, upload files to remote cloud storage. Number 2, download files from remote cloud storage. Number 3, auto-sync files across devices. This is the killer feature. You save a file on your laptop, it instantly shows up on your phone and your work computer. That's it. 3 features. Don't overcomplicate it. Now, a good interviewer might push you. What about sharing files with other users? That's a reasonable scope extension. You can acknowledge it and say, I'll treat that as a V2 feature and focus on core sync first. That's a perfectly valid answer and shows maturity. Non-functional requirements. This is where you show your engineering chops. For Dropbox, these are the qualities that make or break the system. Reliability. We absolutely cannot lose files. Durability is non-negotiable. If someone's business documents get lost, that's a lawsuit. High availability. Users expect Dropbox to always be accessible. We're targeting 99.99% uptime. Low latency sync, she changes distance should propagate to other devices within seconds, not minutes. Scalability, ratum sorted, open we are designing for hundreds of millions of users, potentially exabytes of data. Consistency versus versus availability bunch of inskim. For file sync, we lean toward eventual consistency. It's okay if your phone takes a second or two to get the latest version, as long as it always gets there. Write these down at the start of your interview. You'll refer back to them during your deep dives. Next up, the core entities. These are the objects that get persisted and flow through your APIs. For Dropbox, we have 5 core entities. First, user, who owns and accesses the files. Second, file, the actual content, the bytes. Third, file metadata, name, size, file path, version number, created and modified timestamps, owner. Fourth, chunk. We'll come back to this in the deep dives, but files are broken into chunks for efficient uploading and syncing. Fifth, device. Since syncing is multi-device, we need to track which devices a user has registered. One important distinction, file and file metadata are 2 separate things. The metadata is tiny and queried constantly. The actual file content is huge and accessed less frequently. Keeping them separate is a critical design decision that every strong candidate makes. Now let's design the APIs, keep it simple and restful. First, post to files upload a new file or chunk. Second, get files by file ID, download a file. Third, get files changes with a since timestamp parameter. Get everything that changed since last sync. This is the delta sync endpoint. Fourth, post to files by file ID, chunks, upload an individual chunk. Fifth, get files by file ID, metadata, get file metadata. The sync API is the most interesting one. Clients call it periodically forward or get notified via WebSocket, passing the last time they synced. The server returns a delta, everything that changed since then. The client only downloads what it needs. For uploads, notice we have both a file upload endpoint and a chunk upload endpoint. We'll explain why in the deep dives Stoker synced. It's all about chunking strategy and resumable uploads. Okay, now let's sketch out the architecture. Here's the big picture: client to API gateway to services to storage. Let's walk through each layer. The client runs on your laptop, phone, or tablet. It does two things. It watches the local file system for changes, and it communicates with the backend to upload changes and pull down new ones. When a file changes, the client detects it, breaks it into chunks, and starts uploading. API gateway is your entry point. It routes traffic to the right backend service, handles auth, rate limiting, and so on. Standard stuff. Now here's where we separate concerns into two core backend services. The first is the metadata service. This handles all file metadata: names, paths, versions, ownership. It's backed by a relational database like PostgreSQL. This is queried constantly, so we'll add a caching layer, Redis, in front of it. The second is the file storage service. This handles the actual bytes, important uploading and downloading file content. It's backed by object storage like Amazon S3 or Google Cloud Storage. Object storage is infinitely scalable, highly durable with 11 nines of durability, and designed exactly for this use case. And then there's the sync service. This is the real-time notification layer. When a file changes, other devices need to know. We use WebSockets for persistent connections. The server can push change notifications to clients instantly. We can fall back to long polling for clients that can't maintain WebSocket connections. The flow works like this. Device A uploads a file change. The metadata service records the update. The sync service pushes a notification to device B and device C. Devices B and C call the changes API and download only the delta. Clean, simple, scalable. This is the section that gets you the offer. Let's go deep on the four most important topics. Deep dive 1, chunking. Never upload a file as one giant blob. Always break it into chunks, typically 4 to 8 megabytes each. Why does this matter? Resumable uploads. If your network drops halfway through a 2 gigabyte file upload, you don't start over. You resume from the last successful chunk. Without chunking, a bad connection makes large uploads nearly impossible. Parallel uploads. You can upload multiple chunks simultaneously across different connections. A 1 gigabyte file broken into 128 chunks of 8 megabytes. Each can be uploaded in parallel, dramatically faster than a sequential single upload. Delta sync, the killer feature. When a file changes, you don't re-upload the whole file. You only upload the chunks that actually changed. For a 500 megabyte video where you trim the last 5 seconds, only the last few chunks change. You upload maybe 8 megabytes instead of 500 megabytes. This is huge. Here's how it works technically. The client breaks the file into fixed size chunks. Each chunk gets a SHA-256 hash, and the client client checks with the server. Which of these chunk hashes do you already have? The server responds with what it's missing. The client only uploads the missing chunks. The server assembles the metadata pointer to all chunks. Deep dive 2, deduplication. Every chunk gets hashed with SHA-256 quoting 66 before uploading. That hash becomes the chunk's unique identifier. Before uploading a chunk, the client asks the server, "Do you already have a chunk with this hash?" If yes, don't upload it. Just reference the existing chunk. This is called content-addressed storage. Why is this powerful? If 10,000 users all upload the same popular PDF, you only store it once. The storage savings at scale are enormous. This also speeds up uploads. If you rename a file, the chunks haven't changed, their hashes are the same. Upload takes 0 seconds because every chunk already exists on the server. Deep dive 3, conflict resolution. Here's a tricky scenario. You're on a plane with no internet. You edit a document. Meanwhile, your colleague edits the same document on their machine. When you land and both devices sync, what do? Search Hanara Pasaninskins. There are a few approaches. Last write wins. Simplest, but you might lose data. not great for documents. Conflict copy, what Dropbox actually does. Both versions are kept. The file gets renamed with a conflicted copy suffix. The user resolves it manually. Safe, but can clutter your folder. Operational transform and CRDTs, what Google Docs does for real-time collaboration. Much more complex, typically out of scope for this question. For this interview, go with conflict copy. It's simple, safe, and honest about the trade-off. Deep dive 4, scaling the sync service. At massive scale, hundreds of millions of users, how do you handle real-time sync notifications? Here's the architecture. When a file changes, the metadata service publishes an event to a message queue. Kafka works great here. The sync service consumes these events. The sync service pushes notifications to connected devices via WebSocket. Why Kafka? It's durable, scalable, and handles millions of events per second. If a device is temporarily offline, the events are still in the queue when it reconnects. For the WebSocket layer, you'll need to shard connections across multiple sync service nodes. Use consistent hashing to route a user's devices to the same node, making it easy to push notifications to all of a user's devices simultaneously. Alright, let's wrap it up. Here's everything we covered. Follow the 4-step roadmap: requirements, then entities and APIs, then high-level design, then deep dives. The 3 core features: upload, download, and autosync. Always separate metadata from file content. They have completely different storage and access patterns. Use chunking for uploads, resumable, parallel, and delta sync friendly. Deduplicate at the chunk level using SCHE25ST, Pashte Sarshidi on T56 hashes. Massive storage savings. Handle conflicts with conflict copies. Simple and safe. Scale the sync layer with Kafka plus WebSockets plus consistent hashing. If you're interviewing at senior level or above, the depth you go in those deep dives is what gets you the offer. Show that you understand the why behind every decision, not just the what. If this video helped you out, like it, subscribe, and drop a comment below with the system design question you want me to break down next. I do a new one every couple of weeks. Good luck with your interviews. You've got this. See you in the next one.